Hello, everyone, and thank you for attending this webinar. My name is Linda Hedges, and I am an HPC Specialist Solutions Architect at Amazon Web Services. At AWS, my job is to help customers onboard their HPC applications. Today, I would like to present running HPC applications on AWS using Elastic Fabric Adapter, or EFA. This presentation is a deep dive into EFA, Libfabric, and OpenMPI. You'll also find the information you need to get started using EFA with your high-performance computing workloads. Elastic Fabric Adapter is a network interface for Amazon EC2 instances that enables customers to run HPC applications requiring high levels of inter-instance communications. These are applications like computational fluid dynamics, weather modeling, and reservoir simulation. EFA supports industry-standard APIs, so applications that use a supported version of MPI can migrate to AWS with little or no modification. Here's the agenda for the webinar today. I will start with a quick review of the value of AWS for HPC, followed by a discussion on scalability. EFA is all about scaling your tightly coupled workloads, so we'll talk about some recent Ansys Fluent benchmarks, albeit not run with EFA, so these can give a sense of if and by how much your applications may scale on AWS when running with EFA. Next, I'll introduce EFA, talk about how it works, and also discuss its integration into Libfabric. Libfabric is called by MPI to allow EFA to be run from your application, possibly with no modification to the code at all. We will then talk about getting started with EFA and wrap up with some of our other recently announced HPC services. Before I dive into the presentation, I'd like to thank the AWS team that developed EFA, particularly Brian Barrett, one of the lead engineers who also gave a terrific presentation on EFA at reInvent last year. I recommend you check that out as well. So first, why run HPC applications on AWS? AWS provides you with a virtually unlimited number of architecture and deployment options, allowing you to pick and then only pay for what is best for your applications and your users. As an example, there is no need to over-provision extra memory for all your jobs simply because you have one extremely high memory application. Similarly, pick the storage option that is best for your application and your budget. You can also pick your favorite operating system. Almost all operating systems are available. We have a variety of deployment options with SDKs for scripting and deployment via AWS CloudFormation. Both traditional on-premise style clusters and automatic deploy cloud-native architectures are popular. The agility of AWS allows you to iterate quickly and reduce the time to results. On-premise clusters can take months or more to procure and set up. At AWS, this process takes just minutes. Workloads are burst into the cloud on an as-needed basis, and you pay only for what you use. It is also easy to optimize your AWS infrastructure by swapping in and out instance types or storage solutions to quickly determine the best hardware for your application. The ability to optimize infrastructure means that you can maximize your performance without paying for resources that you don't need. As AWS releases new technology, it's quick to try and migrate the newer capability and then to adopt that powerful capability for your applications. Finally, many customers take advantage of our global footprint, which can allow for increased collaboration with access to clusters from around the world. Here's a quick review of AWS services popular with HPC users on AWS. Starting from left to right, we have two major services targeting HPC users. AWS Batch, a cloud-native service for orchestrating thousands and even millions of jobs at one time, and AWS Parallel Cluster. Parallel Cluster is great for HPC proof of concepts. It is the Swiss Army knife of clusters with as close to a traditional feel as you can get for a cluster in the cloud. Many longtime HPC users are familiar with the NICE products. At AWS, we have both NICE DCV for visualization and NICE Engine Frame available for quick deploy through a CloudFormation template. Nice DCV is in the last box on the right under visualization. AWS has a fast-growing number of storage solutions, from the economical and reliable Amazon S3 for object storage to a variety of different types of elastic block storage or EBS volumes that you can attach to your instances. We have Amazon EFS for shared block storage that crosses availability zones, and now available, and particularly for HPC applications, AWS recently announced Amazon FSx Cluster, a high-performance file system that docks into S3. FSx Cluster offers a low-cost storage solution with the reliability and availability of Amazon S3, combined with a managed Lustre service to be attached to clusters as needed. At the center of the AWS services for HPC is Amazon EC2, where our EC2 instances are optimized for different workloads. You can pick from a variety of instance types, such as a high clock speed instance, compute-optimized instances, high memory instances, even higher memory instances, enormous memory instances, and instances with accelerated processors such as GPUs and FPGAs. Today we will talk about the new C5N and P3D and instance types, as these instances now support EFA. Also, what this presentation is mostly about, we have our network options in the fourth box. Enhanced networking, placement groups, and today we are talking about AWS EFA. At the heart of almost every application, and certainly every application run in the cloud, is the network. Of course, network performance is particularly vital to tightly coupled HPC workloads. The AWS network is unlike most networks used to run HPC applications. It is exclusive to AWS, built by AWS, and designed for really extreme scale. It's also built at commodity pricing, which, along with our Nitro hypervisor, is facilitating the pace of innovation as shown in this chart. While we don't talk about our network a lot, AWS is dedicated to its continual improvement. Just over a year ago, we released the C5 instance with 25 gigabits of bandwidth. Then late last year, the N version of the C5 instance, C5N, was released. The largest C5N instance, the C5N.18x large, offers 100 gigabit networking, which is great not just for bandwidth-bound HPC applications, but also for moving data onto an instance from S3. Note that this is bisection bandwidth within a placement group. It surprises some of our customers that on AWS, there is no network oversubscription. All ports can be run flat out without blocking. Unlike other networks, you don't have a noisy neighbor introducing jitter and interrupting your workload. You're also never your own noisy neighbor, as can happen with large HPC workloads run on other types of networks. Reduced jitter is extremely important for tightly coupled HPC applications, as these applications iterate at the speed of the slowest network connection, not at the speed of the fastest network connection. Reducing jitter is extremely important for increasing application performance. Before diving into EFA, I wanted to talk about scalability in general to help provide a sense of what kind of scalability you can expect from your application. Back in the mid-1960s, Amdahl famously talked about parallel scalability. While he wasn't a fan of spreading an HPC case over a large number of compute cores, his law has now gone on to explain parallel computing and to implicitly lead the development of parallel computing methods. His equation is shown on the right-hand side of the chart. And this equation shows that the limitation to application scalability is the serial time in the denominator of his equation. The serial time or serial work is a work that cannot be parallelized. The greater the serial work, the less it is possible to scale up an application. The serial term impacting scale can come from many places. Commonly, though, it includes algorithm inefficiency, memory bandwidth limitations, as well as latency on the network. Scale-up itself is defined at the bottom of the chart on the right-hand side. Scale-up is the time to run a calculation on one core divided by the time to run the same calculation on many, or n cores. A scale-up of 100, when a case is run on 100 cores, would be perfect or ideal scaling. The scale-up falls off as a function of the serial work, or the inefficiency of the application or compute infrastructure. For example, a scale-up of 90 for a calculation run on 100 cores would be considered 90% efficient. One of the biggest factors affecting scalability is the size of a case. A small case has less computing available to spread over nodes or cores. This means that a small case will generally scale over fewer cores than a bigger case. For a CFD case, the number of cells per core being run on is usually a good predictor of case scalability. Here's an example of a small ANSYS Fluent computational fluid dynamics benchmark. The case size is 1.7 million cells. I must emphasize that for this plot and the following 3 plots, the cases were not run with EFA. I look forward to running these same cases on C5N with EFA in the next few weeks. Here I've defined scale-up as the estimated time to run on one C5 core divided by the time to run on n cores on the particular instance in the plot. So all of the scale-up curves are baselined or referenced to the C5 instant type. The Z1D instance is our fastest clock speed instance with a 4 gigahertz processor speed. It leads the scalability curves with the tallest scaling curve. C5N also demonstrates terrific scaling, though again, these runs are based on C5N without the advantage of the low latency network offered by EFA. I look forward to rerunning this case with EFA. An extrapolation of these curves suggests that the results will be excellent. Similar results are seen for the medium-sized case. At 14 million cells, this case is not quite an order of magnitude bigger in size than the small case that I just showed. Still, relative behavior is similar between the scale-up curves. Whereas for the smaller case, scaling was seen to around 250 cores. Scaling for the medium-sized case is seen to above 800 cores for the C5N instance. Scale-up for C4 is to about 600 cores. Later, when we look at latency numbers for these instances, we'll get a sense of how much latency impacts the scale-up for these cases. Finally, yet another order of magnitude bigger in size, the ANSYS Fluent F1 benchmark demonstrates scalability to above 2,000 cores for this large case. We typically recommend running Fluent between about 50,000 cells per core and 400,000 cells per core, though I expect that Fluent will run well below 30,000 cells per core when using EFA. Again, you can see that the Z1D and C5N instances scale very well for this case, followed by the C5, the M5, and the C4 instance type. But what's better than knowing the scaling behavior of an application? What really matters to the users of HPC software is how quickly will I get my run back and how much did it cost? I encourage you to plot your scaling curves, but to also plot cost versus turnaround time curves and to take a good look at these metrics. Here's an example for the 14 million cell ANSYS Fluent benchmark. Cost is per 100 iterations and is on the horizontal axis. This is the on-demand cost of the run. When run on spot or reserve instance, you can get deep discounts on this price, often paying only 35% of this cost. On the vertical axis is the turnaround time in minutes, again per 100 iterations. This L-shaped curve is typical of applications scaled over a large number of nodes. By looking at a plot like this, you can choose how to run your code. Perhaps you are running 100 cases all at the same time and don't mind waiting an extra hour to get the runs back, because all of the runs are coming back at the same time. Then the very cheapest price makes sense. Occasionally, minutes matter. Perhaps a license is extremely expensive. then the fastest run can be important. Most customers choose to run in the dogleg of this curve, targeting a nice ratio of price to performance. And now introducing the elastic fabric adapter. This section talks about EFA and how it works. EFA is a network device that you can attach to your Amazon EC2 instances to bypass the kernel for fast network communication. With EFA, tightly coupled HPC applications have access to lower and more consistent latency, as well as higher throughput than traditional TCP channels. EFA enhances the performance of instance-to-instance communication that is so critical for scaling latency-bound HPC applications. EFA is optimized to work on the existing AWS network infrastructure without modification to your code, and it can scale depending on application requirements. Most applications will work as is once a supported version of MPI is made available to that application. You can see the EFA logo attached to the C5N and P3DN instances in the chart. EFA is available on C5N.9x large, C5N.18x large, P3DN.24x large instances. Additional instances will be supported soon with plans for releasing M5N, R5N, and also metal instances with EFA. Parallel tightly coupled computing applications are typically based on MPI. Here's a notional diagram of how MPI applications work today on AWS. This is the before chart without EFA. MPI is a standardized message passing interface. There are a variety of versions of MPI, such as OpenMPI and Intel MPI. But these are the two that I will be talking about later in the webinar. MPI is a networking library used by the application to provide point-to-point communication between the different cores on which an application is running. MPI is at the bottom of the user portion of the stack, and it talks to the kernel TCP IP stack, which is at the top of the kernel stack. The kernel stack then talks to the ENA network driver, which communicates with the hardware. Assembling a cluster of instances or nodes, and you have distributed computing. A 4-node cluster looks like this. The application is running on each of the instances and is talking through MPI to the neighboring compute nodes or instances via the network. Even though this is the before picture, this is the configuration used for the earlier scaling plots with ANSYS Fluent. It still works fairly well. Here's the AWS network performance right now and without EFA. Bandwidth is on the left and latency is on the right. We don't publish these numbers as our network is continually getting better, even for our older instances. But anyone can get onto AWS, put 2 instances in a placement group, and run the OSU bandwidth and latency benchmark to get this result. On the right, the latency shown is that across each instance in the same family in a placement group. For example, it's the latency of a C4 talking to a C4 and the latency of a C5 talking to a C5. You can see that latency gets better with each generation of instance. Even moving from C5 to C5N without EFA shows a drop in latency. EFA will drop this latency even further, as you'll see in a few charts from now. Bandwidth is on the left. The blue curve is the bandwidth across the C5 instance. You can see that 25 gigabits, the bandwidth is about 2.5 times that of the bandwidth across C3 and C4, which each have 10 gigabit networks. The green line is the bandwidth for C5N without EFA. It is harder to drive the full 100 gigabit bandwidth with a simple MPI benchmark. We've done it and we'll release it in a white paper on how to do that. But what we'll see in a moment is that with EFA, driving 100 gigabits with MPI is much easier. Here's the stack with EFA. It is similar to the before stack, but you can see that the MPI communication now bypasses the Linux kernel and the ENA stack. This is done with a library called by MPI that is called Libfabric. Libfabric then talks directly to the EFA hardware. And here are 4 nodes strung together with EFA. To the application, this cluster stack looks identical to the before cluster stack. The application is still run the same way with MPI run. It's run on the same hardware as with C5N, still using a placement group. But now there's an extra network device called EFA that allows MPI to talk to the networking hardware directly to lower both latency and jitter. And this is the same chart as before, but C5N is now shown with EFA attached. Bandwidth on the left is approaching 100 gigabits with an MPI application, and latency has dropped even further. Still though, microbenchmarks don't tell the whole story. What's not being shown here is a reduction in jitter. Applications perform at the speed of the slowest network connection, not the fastest. The best way to know how your application will perform is by testing it with C5N and EFA. Correlating this plot with the earlier ANSYS Fluent benchmarks show that we can expect to be scaling larger latency-bound applications into the thousands of cores. I'm really looking forward to trying EFA at scale. In this section, I'll talk about Libfabric, OpenMPI, and Intel MPI. AWS actively supports both the development of OpenMPI and the Open Fabrics Alliance that creates Libfabric. There are many implementations of MPI. Libfabric is the magic that lets your application talk to the EFA hardware through the MPI version of your choice, without the heavy lift of having to tailor each version of MPI to the hardware. This diagram shows how Libfabric works. Applications interface with the upper-level protocols, such as MPI or SHMEM, which rely on Libfabric to communicate with the hardware. On the bottom, Libfabric has a robust developer community supporting it. In addition to AWS, other suppliers like Intel, Cray, and Cisco are also contributing to the Open Fabric Alliance. Libfabric alleviates the burden of defining this interface for every version of MPI that our customers would like to use. Because of this, the time required to develop performance improvements is shortened. Libfabric is ideal for Amazon because in addition to supporting the majority of MPI implementations, it is also independent of the underlying hardware. This gives Amazon the opportunity to invent at the hardware level and to get these innovations passed on to our customers quickly. For the first half of 2019, customers will use an AWS custom version of Libfabric, but sometime in 2019, Libfabric version 1.8 will be released and will support EFA out of the box. As with the Open Fabric Alliance, AWS is actively working in the OpenMPI community. Our goal is to ensure that OpenMPI works reliably with AWS HPC services on an ongoing basis. We're not just throwing code over the wall, but taking ownership in the open source community. We've already made changes to help OpenMPI better use EC2's unique network, and as you can see, Brian Barrett of AWS was the release manager for version 3 and 3.1 of OpenMPI. Installing the latest version of OpenMPI on an Amazon instance is quick and easy. For distributed computing, I prefer to install OpenMPI to my home directory. Sometimes I do this with user data and with a little snippet of code in the chart. The home directory is then shared out amongst all of the compute nodes. OpenMPI can also be added to an AMI to use on all of the compute nodes, or perhaps placed on a shared software drive or a shared data drive shared out to the compute nodes. Once on a shared drive, a snapshot can be can be made, and this allows for the quick rehydration to a new volume for deployment to multiple clusters. The OpenMPI website, shown in the upper corner, is full of information about OpenMPI. Links can be found to both the software download folder and also to the documentation. I encourage you to take some time and check the documentation for MPI Run or MPI Exec. It is a great way to review which flags you are using and to make sure you are getting the best performance for your application. In particular, it is important to double check that you are binding processes to cores and that you are not oversubscribing the instances with more processes than there are cores. This can be checked with both the report bindings flag in OpenMPI and also using the HTOP utility to monitor the job progress. AWS has also been working with Intel on improvements to Libfabric. We expect Intel MPI to be ready to interface with EFA with their 2019 U1 release in Q2 of this year. The Intel MPI runtime libraries are free to use with your MPI applications and are also easily installed with both yum and apt-get installs. Shown here is the yum install commands, which can be found at the link at the bottom of the chart. By default, Intel installs the MPI libraries to /opt. Sometimes I simply install Intel MPI to all of my compute instances with user data and the little bit of code above. It is also easy to share out the /opt directory or to link the /opt directory to a shared volume on each of the compute nodes. The Intel documentation is extremely comprehensive with webinars and tutorials to learn more about the MPI commands and how to get the best performance from your application. Getting started with EFA. You need 4 things to make EFA work. First, you need a supported platform. There are 3 instance sizes today that we've already talked about, the C5N18X, the C5N9X, and the P3DN24X. Next, you need a kernel module, which can be downloaded from our GitHub site. The link is there, or it's already available in Amazon Linux and Amazon Linux 2. We are working with the other Linux distros to include the EFA drivers as part of our Quick Start AMIs on AWS. Next, you need the Libfabric stack. For the first half of 2019, it'll be an AWS custom version, and then when Libfabric releases its version 1.8, Libfabric will include EFA out of the box. Finally, you need a version of MPI with the Libfabric driver, such as OpenMPI 3.1.3 or later. Other versions of MPI, such as Intel and MPICH, will be ready soon. There will be an installer script that you can run after starting up an instance that will perform these steps for you, so check the EFA documentation for that script. To begin with, the script will support Amazon Linux, Amazon Linux 2, CentOS 7, and Red Hat 7. There are a few constraints required with this release of EFA. I don't think any of these are a true constraint for the typical HPC workload. The first is that EFA communication is confined to just one subnet. If you have 2 instances in 2 different subnets, even if they both have an EFA device, they can't talk to each other. The second is that you have to add a security group to both the ingress and egress rule of a security group to allow all traffic between instances. If that's confusing, then you'll want to refer to the EFA documentation because this point is critical. The third constraint is that there is a limit of only 1 EFA NIC per instance. And the final constraint is that EFA NICs can only be added during the launch of an instance or to a stopped instance. Many of our HPC customers launch compute clusters via the EC2 run instances command combined with a little bash scripting. The EC2 run instances command is part of the AWS CLI. This command will build a 4-node cluster. You can see that with the compute node count of 4 near the top of the command. The instance type selected is next a C5N.18x. Right below the instance type callout is the CPU options flag. This offers a quick way to disable hyperthreading. Hyperthreading is enabled by default in the cloud, and most HPC applications will run best with hyperthreading disabled. Next, the region called out is US East. A real AMI ID would be required. I've added a role to the instance. A key name is used for SSH login. Both the key name and the role and the placement group, which is next, need to be created before launching the instance. Tightly coupled applications will definitely want to use a placement group. If you have user data, it can be added with the user data flag. The driver and Libfabric install script, for example, could be added to that user data script. And finally, the network interface flag is used to call out the EFA device. You can see that in the orange ellipse. And so this is the big difference between the AWS CLI command today and how it was before. When launched this way, without a security group specified, the instance will pick up the default security group. So make sure that the default security group, or whichever security group is chosen for your launch, includes the name of the security group itself in the ingress and egress rule. And that's it. That's all it takes to launch EFA. After launching this command, you'll see a bunch of JSON scroll by, and we get our cluster, which looks like this. You'll see 4 C5N.18x large instances with the EFA devices already attached. There are other ways to launch an EFA cluster. Launch templates already support EFA. The launch template syntax is seen here with just the addition of the network interface key pair in the orange ellipse. Launch templates will let you deploy clusters with AWS CloudFormation based on auto-scaling groups with AWS Batch and for spot fleet requests. Again, it's very simple to add EFA to your existing clusters if they are based on launch templates. Notice also that launch templates give you an easy way to disable hyperthreading via the threads per core key pair near the bottom of the launch template. A value of 1 signifies that hyperthreading is to be turned off. While EFA may have been the most exciting HPC service announced at reInvent, we announced 2 other services that are great for HPC. AWS Parallel Cluster is an AWS-supported open-source cluster management tool that makes it easier to deploy and manage HPC clusters on AWS. If you are familiar with CFN Cluster, AWS Parallel Cluster is the official AWS service based on CFN Cluster. It automatically sets up the required compute resources, a shared file system, and offers a variety of batch schedulers, such as with AWS Batch, SGE, Torque, and Slurm. While it is fundamentally a traditional cluster in the cloud, it has the added benefit that it can spin up compute resources as needed when jobs are submitted to the queue. When a job completes, compute resources automatically spin down, so you don't have to pay for idling compute nodes. AWS Parallel Cluster is terrific for both proof of concepts and production deployments. While EFA is not yet available in Parallel Cluster, we expect to release it imminently. Another very exciting release for HPC at reInvent was the announcement of Amazon FSx Lustre. Amazon FSx Lustre is a high-performance file system. While Lustre is far from new to the HPC crowd, FSx Lustre is a fully managed service, which means that you don't have to fiddle with it and maintain it to use it. It creates and configures file systems that are highly durable and available in minutes. It protects your data with daily automatic backups. It is fully managed, so the administrative overhead of setting it up, patching it, and provisioning file servers is eliminated. It allows for applications to access hundreds of gigabits of data per second, millions of IOPS, and sub-millisecond latencies. A really great feature with FSx for Lustre is that it works natively with Amazon S3, making it easy to process cloud datasets with high-performance file systems. By linking it to an S3 bucket, the file system transparently presents S3 objects as files and allows you to write results back to S3. Finally, I'd like to point out some resources for getting started. First, as I mentioned before, there's a terrific deep dive on EFA presented at reInvent 2018. I highly recommend watching it. You can search the web for it or go directly to YouTube to find that video. For EFA specific information, don't forget to check out the AWS documentation for that service. And for general information on HPC on AWS, you can go to the AWS HPC homepage listed here. You'll find lots of webinars and white papers at that link. I've also included the link for the HPC Well-Architected Lens white paper. That's a great source for an overview of HPC on AWS. And last but not least, the Amazon AWS Getting Started pages are always a fun place to take a few 10-minute tutorials on many of our services. This is a great place to start as well if you've not used AWS before. With that, thank you for your time. I'm excited to use EFA and I hope you are as well. Let's see if there are any questions.